Now this is the final section in the further kinematics chapter on integrating vectors, and I've already given an introduction to this in the last section 8.4 about integrating vectors, so I'll just run through it quickly again. So if we use R for position, if we use R dot for the velocity and R double dot for the acceleration, so we're looking at what happens when we go this way, so that's integrating. So R dot here, this is what you get when you integrate R double dot with respect to t. That could also be written as that you're integrating the velocity vector, sorry, the acceleration vector with respect to t. If you use the alternative notation, that is if you use a there and v here, and you may use s there, and over here you can say that, well, the position displacement is when you integrate r dot with respect to t, or you could write that as when you integrate the velocity vector with respect to t. Yeah, so we've got different ways of using no notation, but I did say on the last video that as you integrate, you introduce a constant of acceleration. Yeah, now we don't just put plus c, but our constant of acceleration is going to be made up of two parts, an I part and a j part. Yeah, and then if we integrate again, then we'll introduce maybe two new constants if you don't work out the previous ones. Yeah, but what you need to realize is that when you get this new, when you get your new constants, it's made up of an I part and a j part. And just like differentiation, when you integrate the bits which are in front of I first, and then you integrate the bits which are in front of j second, and so you do them almost like separately. But we'll have a look at an example, and normally in a question there's some sort of information that allows you to work out this constant here before you move on to the, maybe if you need to integrate again, before you move on to the second bit. A particle is moving in a plane at time t seconds. Its velocity is given by this vector here. T is positive. When t is 0, it tells us that the position is this. Find the position of the vector b at time of find the position of the vector p at time t seconds. Right, so what have we got? We've got the vector, which we could write as r dot 3ti plus half t squared j. We need to work out the position vector, so you could use s or you can use r like that, and that's going to be equal to what we get when we integrate our velocity with respect to t. Let's write that down here. So if we do that, we're going to have 3 over 2 t squared I. Yeah, add 1 to the power, divide by the new power. Plus, now if we add 1 to the power, it becomes t cubed. A half divided by 3 is 1/6. So 1/6 t cubed j. Then plus ci plus dj. Yeah, so this bit is like our constant of integration. Now we're told that when t equals 0, the position vector r is equal to I minus 3j. So we now substitute in t equals 0 and make it equal to 2i minus 3j to work out what our constant, our vector constant is. So if I do that, so it'll be 3 over 2 times 0 squared I, because t is 0, plus 1/6 times 0 cubed j, plus ci plus dj is equal to 2i minus 3j. Right, so from that we should be able to work out what c and d are. Now can you notice that all of this becomes 0, so that means that c is 2 and d is -3. So our full expression for our position vector is, now we've got this so far, now we've also got +2 for I, so we're going to put this I bit and this I bit together, so we get 3 over 2 t squared plus 2, that was the constant of integration, I, and then for the j part we have this 1/6 t cubed, and then we're going to put the -3 there as well, because that's the j up part of d, constant of integration, so you get 1/6 t cubed minus 3j. So you group together the i's and the j's, and what we need to do is to find when t equals 0, find the position of the vector at time t. That's it then, we don't need to substitute anything in, and because it's a position vector it's going to be in meters, so we can stick an m at the end if we stick it all in brackets, and there we go, that's our position vector. Particle is moving in a plane, so that at time t seconds its acceleration is this. Okay, so that's r double dot there. When t is 3, the velocity is 6i and the position is 20i plus 3j, so that's also at t equals 3 with respect to a fixed origin O. Part A, find the angle between the direction of motion of p and I when t is 2. So the first thing we need to do is to find out what the velocity vector is. We can use that to find its direction of motion. So the acceleration vector is 4i minus 2tj. So the velocity vector is going to be what we get when we integrate the acceleration vector with respect to t. That means integrating this 4i minus 2tj with respect to t. So if we do that, we will get 4 will become 4ti. The minus 2t will become minus t squared j. Then we have our constant of integration, so ci plus dj. It doesn't matter which letters you use, a, b, c, d. Now we're told that when at time equals 3, the velocity, so r dot is 6i, so we can substitute that in to find the constant of acceleration. So that will be 4 times 3, so substituting in t is 3i, minus 3 squared j, plus ci plus dj is just 6i. So I'm going to write that as 6i plus 0j. Then I'm going to compare the I terms and j terms so I can work out what the constant of integration is. So I've got 12i on the left plus ci equals 6i. Okay, so that tells me that c is -6. And then if I compare the j parts, I've got negative 9j plus dj equals 0j. So that means that d is 9. So my full velocity vector with the constant of integration is going to be, now I've got 4ti, so 4ti, and then I've got this negative 6i from a constant, so negative 6i. Okay, so this was what was there before this bit, and that's the constant, so you put the I bits and the j bits together, plus my j bit is negative t squared and the constant is plus 9, so there's all my j bits put together. So that's my full velocity vector. So what I want to do is to find out what's the velocity when t equals 2, and then I can find the direction when t equals 2. So if I just put here at t equals 2, I will get the velocity will be, let's work it out, 4 times 2, 8 minus 6, which is 2, so 2i. And for this bit, that'll be 2 squared, which is 4, negative 4, plus 9, which is going to be 5. So that'll be plus 5j. So this is the velocity at time equals 2. I want to find a direction, so always draw a diagram. So here's my axis, and it's a vector that's 2 across 5 up, doesn't need to be to scale, 2, 5. So the velocity vector looks like this, and I want to find the angle between that and the I vector, so that's the angle I want to find. So that tells me that I want to do theta is going to be the tan inverse of the opposite, which will be 5 over the adjacent over 2, so the tan inverse of 5 over 2. Now if I do that, and remember we go back to degrees, so if you're in radians, make sure that you go back to degrees, and tan inverse 5 over 2, and I get to 1 decimal place for angles, 68.2 degrees. So 68.2 degrees, that's the angle it makes with the vector I at that particular time. Okay, part B of the question, let's just rule that off. So part B says the distance of P from O when t equals 0. Right, so now we need the position vector. So to get the position vector R, we integrate the velocity vector with respect to t. That means we're going to integrate R 4t minus 6i plus negative t squared plus 9j with respect to t. So let's do that. So 4t will become 2t squared, so 2t squared. Negative 6 will become minus 6t. Okay, so that's the I part. And the negative t squared will become negative a half t cubed. Is that right? No, negative a third t cubed, sorry. So plus negative a third t cubed, and then the 9 will become 9t j. Then we have a constant of integration, so we've already used c and d, so let's use e and f. Okay, I could have used a and b, it doesn't really matter. And we were told right at the very start that when t is 3, that's the position. So now we're going to substitute that in, and we'll say at t equals 3, r equals 20i plus 3j, so that can get substituted in, and we'll see what we'll get. So if I put the 3 in, we'll just work this out manually. So 2 times 3 squared is 2 times 9, 18. So I'm going to have 18 minus 18. Is that right? 2 times 3 squared, 2 times 9 is 18, minus 6 times 3, yeah. So we end up with 0i. There, okay, just double checking. Here, I think I'll use a calculator for this bit. Actually, I don't think I need a calculator. Right, so 3 cubed is 27. A third of 27 is 9, so I've got negative 9 here. So negative 9 plus 9 times 3 is 27, so I've got negative 9 plus 27 is going to be 18. So I've got plus 18j plus ei plus fj, and that's going to equal 20i plus 3j. So I can work out what my constants are. So looking at my I terms, 0 plus e equals 20. Let's write that down. So 0i plus ei equals 20i. So that means that e is 20. And then for the other bit, we have the j bits, 18j plus fj equals 3j, which means that f equals negative 15. Right, I'm running short of space here, so I might need to go, I'm going to go right to the top of the page. So I'm going right up here because I've got no space left. So my full position vector r is going to be, now what did I have before? So I've got this 2t squared minus 6 plus 20. Right, so let's write that down. 2t squared minus 6t plus 20. The 20 was the constant I, plus 1/3 t cubed plus 9t minus 15j. Okay, so that's my full direction or position vector, and I want to find the distance of P from O when t equals 0. So what we're going to do is we're going to put in t equals 0 to find out what its position is, and we need to find the distance between that position and its position here. Well, actually not its position there, because that's the position when t equals 3. So let's just substitute the t equals 0 in. So at t equals 0, what do we get for r? Oh, and actually we just need to find the distance of P from the origin. So actually we'll get the position of R from the origin, or the position of P from the origin, and we just do Pythagoras on it. So it's actually not that bad. So plugging 0 in, that's gone, that's gone. So I'm just left with 20i. So equals 20i. And with the second bit, if t is 0, that's gone, so that just leaves me with negative 15j, negative 15j. So if I want to find the distance from the origin, I just need to find what the modulus is of that, which is going to be the square root of 20 squared, little tiny bit of space here, plus negative 15 squared. And let's do that before this pen gives out. So square root 20 squared plus negative 15 squared, or just 15 squared, and I get 25. So just about enough space to write down an answer of 25 meters. So that is our final answer here. So let's just highlight that. So let's highlight that there for our answer for C, just in case you've lost your working. And our answer for A we've done, and that's it. The velocity of a particle p at time t seconds is given by this expression here. When t equals 0, the position is given by that, so I'm just going to mark there, that's when t equals 0. That's basically what r is, isn't it? R is 2i minus 4j. Find the position vector of p after t seconds. Right, so we have the velocity vector, which is this 3t squared minus 8i plus 5j. We want the position vector, which means integrating the velocity vector with respect to t. That means integrating this 3t squared minus 8i plus 5j dt. So that will give us 3t squared becomes t cubed minus 8ti plus 5tj plus a, let's just use a and b, and bj for our constant of integration. Now we're told that when t equals 0, r equals 2i minus 4j. So let's plug those in so we can work out what a and b are. So if I put 0 in this, I'll end up with 0i. And if I put 0 here, I'll end up with 0j. So 0i plus 0j plus the a, I and the b j part equals 2i minus 4j. So what that means is a must equal 2 and b must equal negative 4. So my full vector for my position, and I'm going to group the i's and j's together. So that means I need to take this up here. So I've got t cubed minus 8t plus 2i. So t cubed minus 8t, then plus the 2, which is the constant of integration, I. And then for the j part, I'm going to have 5t minus 4, because that's the constant part, j. So find a position vector of p after t seconds. That's it. So let me just highlight that answer before we go on to part B. A second particle, q, moves with constant acceleration, constant velocity, right, so this is constant velocity, this one. When t equals 0, the position vector of q with respect to the origin is 2I meters. Prove that p and q collide. Now remember, we had that thing that said that the final position is equal to the initial position plus the displacement. So we could say that the position of q is this position plus this velocity times time. Yeah, we had this thing which was r equals r0, the initial position, plus the displacement, velocity times time. So let's just do that. Now because we're dealing with q, let's call this r sub q, and we'll put r and we'll put a little sub p there so we know that we're dealing with q. So that's going to be its initial position, which is 2I plus 8I plus 4j t, and let's put the i's and the j's together, so we get position of q is 2 plus 8ti, expand the brackets, plus 4tj. Now if these things are going to collide, then that means the position of RP, or position of P, is going to equal the position of Q. Now we've got expressions for both of those, so we're going to set those equal to each other and see if we can find a value of T that balances it. Then we know that they collide and we know at what time they collide. So RP is this T cubed minus 8t plus 2I plus 5t minus 4j, and that should equal the 2 plus 8ti plus 4tj. So we solve this by equating together the I parts and the j parts. So let's do the I parts. So we'll have t cubed minus 8t plus 2 equals 2 plus 8t. We can rearrange that to give us t cubed, and we'll take away 8t from both sides, minus 16t, and then take away 2 from both sides equals 0. We can factorize that, so we get a t outside the bracket, and then t squared minus 16. So this will give us either t is 0 or t is 4 or t is negative 4. Right, so straight away we can discount this one because t is positive. So they're either going to collide when t is 0 or t is 4. The way we're going to find that out is now equate the j parts. So that will be 5t minus 4 equals 4. So that's 5t minus 8 equals 0, which means that will give us t equals 8 over 5. Spotted a mistake. Let's go back. 4t. Now I'll just put 4, so that should be 4t because I've got 4t here, because I tried solving it and then realised, hang on, it doesn't work. That was my mistake. So if we take away 4t from both sides, we'll get t minus 4 equals 0, which means, there we go, it works now. T equals 4. So the only solution which is the same for both is t equals 4. So then we say something like they do collide at t equals 4 seconds. So I'll just highlight that. Right. You should now be able to do exercise 8E on pages 175 to 177.